Imagine a big glass sphere so you can see what is happening inside. Imagine a triangular prism with its four corners touching the inside of the sphere. Imagine that, instead of a prism, we have a cube inside the sphere. Again, all of its corners are touching the inside of the sphere. Now, imagine that instead of a cube, we have a bigger object inside the sphere that has an even much larger number of sides. Again, all of its corners touching the inside of the sphere. It's a bit like one of those black and white panel footballs that when you blow it up, it gets rounder and rounder. You can see that as the number of sides increase, the object inside the sphere is becoming more like a sphere itself. But we don't want to go crazy trying to work on figures with a very large number of sides in 3 dimensions. That would be a bit difficult to draw and explain. So let's make it easier by choosing a number of sides that we can handle. Also, let's think of it in 2 dimensions by slicing the sphere right down the middle. I am going to show you a few tricks. To make things easier, I am going to choose a slice that gives us 8 sides for our 2-dimensional view. It makes it easier to see how the object inside the sphere is made up of different bits. It also makes it easier to calculate the surface area. In the above slide, you can see that the object inside the sphere is made out of 2 cones and 2 frustums. Frustums are simply cones with their heads chopped off. I remember the name by thinking of them as frustrated cones because they really wanted to be full cones, not just a bit of one. Now let's add some labels so we can do the maths. I have been very careful in choosing my labels so it is easier to understand some ratios and the final calculations. Label the diameter D and the radius R. Label the chord highlighted as M because we are going to move it. Label the side S, label the angle theta, and label the arc subtended by theta as A. Now let's see what happens when we double the number of sides. Doubling the number of sides means that whilst the diameter D of the sphere stays the same, the angle theta is bisected and the length of the side and the arc is similarly halved. But look what happens to the chord M. This has become a little bit longer and is moving closer to the diameter. Remember, I called the chord M because it moves as the angle gets smaller. You can see what's coming next, can't you? As the number of sides doubles, M gets closer and closer to D until M eventually ends up the same size as the diameter D. So as theta gets closer to 0, M becomes equal to D. In a similar way, the length of the side S gets closer to the length of the arc A. So as the number of sides increase, the object inside becomes a tight fit in the sphere. Now let's look closer at our 8-sided figure. You can see that it is made up of 2 similar cones and 2 similar frustums. We aren't going to prove the formula for the surface areas of cones and frustums here. If you want to, you can find many ways of doing so on the internet. I have put a version on my YouTube channel, Maths Education. One way of expressing the surface area of a cone is to say it is pi times the radius of the base, which is usually called r, times the slant height, which is usually called h. So the surface area of a cone is often written as equal to pi r h. One way of expressing the surface area of a frustum is to say it is pi times the slant height times the sum of the radius of both ends. So the surface area of a frustum is often written as pi times, in brackets, r1 plus r2 times h. Now looking at our diagrams, and using our labels, we can write that the surface area of each cone is equal to pi times x times s, and the surface area of each frustum is equal to pi times x plus y times s. So let us write down the total surface area of our 2 cones and 2 frustums. Call the total surface area SA. So SA is equal to 2 times xs plus 2 times pi times, in brackets, x plus y times s. When you multiply out the brackets and simplify, SA equals 2 times pi times s times, in brackets, 2x plus y. At this point, take a deep breath and tighten your seatbelt because it's going to get a bit complicated. Now is a good time to get some refreshments. Either refresh your memory about angle, circle, and triangle rules, or if you are confident in using them, just get a drink. For those who want their memory jogging, here are a few rules about angles. Just hit the pause button if you want to revise. Here are a few rules about circles, and a few more rules about circles. Here are a few rules about triangles. Refreshed? Now let's go back to our 8-sided figure and use some of these rules. We want to find values for x, y, and d so that we can show the surface area SA in these terms. Using the alternate angle rule, angle 1 equals angle 2 equals angle 3 equals angle 4 equals angle 5 equals angle 6. Using the circle rule that the angles subtended at the circumference are equal, we can show that angle 6 equals angle 7. The corresponding angle rule shows that angle F equals angle G equals angle H. If a chord is a diameter, the angles subtended at the circumference are not only equal, but are all 90 degrees. So we can mark the angle between M and S as a right angle. We can use the rule about a diameter bisecting the circle chords to label more of the sides of the other triangles. Finally, we can use the rules regarding triangles that have the same sides and angles to label the remaining angles and sides of the triangles. I deliberately labeled the bisected chords with small x's and y's, and the base areas of the triangle sitting on the diameter with big x's and y's, so that the next bit of maths is easier to understand. I hope it works for you. So let's extract from the diagram the 4 shaded triangles and compare them. By using various rules, we show that all 4 triangles are similar, having equal angles. The 2 triangles highlighted with big X as the base have equal angles and sides, and are congruent. We can look at these triangles closer now, and we can compare them. To make it easier to find some ratios, I have turned the biggest triangle round a bit. As all the triangles are similar or congruent, we can write down some simple ratios. Taking the ratios, you can rearrange them to give 2 simple expressions for x and y. X equals m times big X over s. Y equals m times big Y over s. Using our labels, we have shown that the diameter d is equal to 4 times big X plus 2 times big Y. The radius r equals d over 2, so d over 2 equals 2 times big X plus big Y. Now let's substitute for x and y in the expression we worked out for the total surface area. Remember we showed that SA equals 2 times pi times s times, in brackets, 2x plus y. So we can now write SA equals 2 pi s times, in brackets, 2m big X over s plus m big Y over s. Canceling out the s and taking the m out of the brackets gives us SA equals 2 pi m times, in brackets, 2 big X plus big Y. But we already showed that 2 big X plus big Y is the same as d over 2. So we can write down the surface area as SA equals 2 pi m times d over 2. Now the trick is that we have already found that as the number of sides increase, m gets closer and closer to d until it becomes the same size. We can now write the surface area by substituting d for m, so SA equals 2 pi d times d over 2. We haven't finished yet, because mathematicians like to write these sort of things using the radius. So as d equals twice the radius, the formula becomes SA equals 2 pi times 2r times 2r over 2. Canceling out the 2's and simplifying gives us the surface area of the sphere is equal to 4 pi r squared.